Good morning and thank you for taking the time to attend this presentation. My name is Dr. John Kenny and I am the founder of Grimsledge Engineering Solutions. So recently we won a Innovate UK award to develop and try to apply some algorithms that we developed for intelligent monitoring purposes to home health devices. And we believe we've came up with some interesting results which we want to share with you today. So before we get onto that, I'm going to tell you a bit of a story about how I got into this in the first place and the reasons behind it. Then we're going to move on to how the system works. And finally, I'm going to show you some interesting results and how they might be applied in a few different industries. And then we can have a chat about what you think about those results. As healthcare systems have become increasingly stressed and the expectation of what these healthcare systems can deliver has become greater, there's been a significant migration of health and medical devices into the home. It is also vital to balance the range of relevant information with a simplicity of presentation to allow easy assimilation by clinicians or indeed by autonomous systems. As healthcare data is relative to the patient, it is important to track changes over hours, days, months and years without increasing the workload of the clinician. This work will address the issue by developing a novel algorithm to detect subtle changes in complex physiological signals, enabling autonomous alert triggering, early intervention and informed decision making in real time and in long-term monitoring. The novel algorithm will be suitable to be embedded directly in a smart device, such as a smartwatch, a standalone IoT hub, or in the cloud as part of a larger digital health framework. Some time ago, my wife gave birth to two little girls you can see here. They are monozygotic identical twins, but one was born with tetralogy of Fallot, which means she had a hole in her heart. At 3 months old, she had a BT shunt fitted, and then at 9 months old, she underwent heart surgery and had a patch placed over the hole. My daughter is recovered and is very healthy, as you can see. But as you can imagine, this was an extremely stressful period for us as a family. And one of our major anxieties was, and still is, what happens if her condition degrades and we don't recognise it? What if her heart health gets worse over time? Or what if she gets an infection and we don't notice until it's too late? What if the patch or a valve in her heart fails or begins to fail? What if this? What if that? You have these concerns all the time. What I really wanted to know was, how can I monitor to ensure that she's okay, right? Well, I'm an engineer, so I started thinking of ways to do this. I also started working with a lot of med tech companies, helping them in any way I could. I started looking at wearable med tech, PPG sensors, ECGs, the stuff you'd find in smartwatches. And during this period, I heard a lot of clinicians say things like their blood oxygen saturation is low, but that's normal for them. Or this is low, or this has changed, but that's normal for them. Or the respiratory rate is low, but that's normal for them. And I thought, well, if I could monitor the normal, then surely anything outside of this normal is an indication that things are changing, whether for better or worse. So then I thought, well, if I can crack this, then that's going to be something that could be useful in all walks of life. So I thought, well, if this could help my daughter, then surely it could help someone recovering from surgery. It could measure the norm before they go home, and then if it changes, then you could raise an alert to allow them to go see their clinician and get checked up. And the same sort of could be said about infections. Well, could I track an infection? Could I detect when someone got an infection and fought that infection off and then went back to normal? And could we use that data in a meaningful way? This led on to thinking about general sickness, injuries, fatigue, mental stress. And then I thought, well, what about long-term health over years? If you can wear this thing every day, like a watch, then you could monitor heart health over years. You could then implement your own lifestyle changes if you notice your heart health getting progressively worse. And then I thought about the opposite. Well, if you can monitor a condition getting worse, then surely you could monitor a condition getting better. For example, fitness. And then I started asking these questions like, could you quantitatively monitor someone's fitness improving in a very personal manner? And then I thought, okay, well, if I could do that, then could I use this system to indicate whether someone was fit, or at least that they're normal? And if so, how could we use that? For example, in the military, could I say when a soldier was fit for duty, or a maritime engineer was properly rested during a trip away at sea? Could it tell whether a patient was in good condition prior to complex surgery to give them the best opportunity to have their surgery and survive their surgery? These are all questions that I was thinking about when I came into this project, and they all hang on that one problem. Can I monitor that change? Can I monitor a change in someone? So being happy with the problem that I was trying to solve, I started looking into ways to solve it. So at the proof of concept stage, I wanted to find a method that might answer some of these questions. And the first thing I did was have a look at wearable medtech to see if something was already available, and it was. PPG sensors, wearable ECG sensors, have been integrated into smartwatches to monitor heart rate for quite some time now. And in fact, most people in this room are probably wearing one. Unfortunately, the heart rate itself can only tell you so much. A lot of these sensors don't output the raw data, and I wanted the raw data. So I got in touch with Maxim Integrated and started looking into building my own prototype that would give me access to the data I wanted. Now, most people will be familiar with PPG sensors, but for those who aren't, then I'll give an extremely fast overview. So PPG sensor even transmits light of a specific wavelength into the skin and surface tissues. The light is scattered and absorbed by the tissues and fluids. And as the blood is pulsing through your skin and surface tissues, as it increases and decreases, it modulates the received signal, giving a representation of the heart activity. Now, the prototype health band I put together had two green PPG sensors on it. It had an IR PPG sensor and a red wavelength PPG sensor. It also had a 3-axis accelerometer to monitor movement. It had a small digital signal processor on there, a Bluetooth module, some memory, and a battery. We had a number of volunteers who agreed to wear the band for us. They wore the band throughout the night so that it would record them when they were asleep. We took the reference period from when they were in their deepest sleep periods, when they were at their absolute most restful state, and then we compared that with the rest of the data that was produced during the nighttime period. So what we have here is the accelerometry with the X, Y, and Z axis with the magnitude in black. What we can see is these flat periods where there's very little movement indicate that the volunteer is likely asleep. Now we see these odd spikes in the data here, which indicates that the person has just rolled over in their sleep, moved their arm, or a very sort of slight movement. We get this very noisy band of data at the beginning, which is when they're getting ready for bed. Main data that we need is the PPG. So we've got two co-located green wavelength sensors, and we use these two co-located sensors to remove some of those motion artifacts we talked about. So we've got two co-located green wavelength sensors, and this is the typical data that you get off. This is about 7 hours worth of data. We've got the infrared and the red wavelength sensors. So these are going to be different. These penetrate different depths into the tissues, and these are generally used for calculating oxygen concentration. Well, we've got our derived heart rate directly from the PPG tracers. So you can see with this person, when they were first getting ready for bed, their heart rate was up around 83-ish, spiking, what you can see there, spiking up. and then dropping down and then peaking and dropping during the night as well. So we take our raw PPG data, which we saw earlier, and we put it through a high pass filter and a low pass filter, and we get the DC component, we get the AC component, and then we normalize the AC component with the DC component, and we get what's called the normalized pulse amplitude, which gives us a very nice clear trace. What we do then is we take the normalized pulse amplitude, which you can see here, very neat and tidy, and we take the first derivative of that, and then we take the second derivative of that. We then take the power spectrum. The frequency for this is 0.5 Hertz to 5 Hertz. And then we take the first derivative, which highlights the higher frequencies, and then second derivative, which further highlights the higher frequencies. We then calculate the heart rate distribution across each sample period. We take the IBI distribution. So the IBI is the interbeat interval. We then take the end-to-end sample interval of the interbeat interval. So what this is looking at is the change between each sample. We calculate and record the SpO2 concentration distribution. And again, we have the end-to-end distribution. So we expect this to be quite small if you're only getting very small changes between samples. So that's all the data that we're collecting from the volunteer. So how do we use that data to monitor change, to monitor whether something is varying from the volunteer's normal? So what we do is we build up a reference profile. So we take all that data every 60 seconds throughout the night, and we overlap it as well. So there's a 30-second overlap. So we're getting quite a lot of data there. And what we're doing is processing that for a whole night. And then we are using that to build up a reference profile or a rest profile for the volunteer, which we can see on the top here. So this is a IBI profile, IBI distribution profile for an entire night when the patient was not moving. So either asleep or at rest in bed. Now this down here is a 60-second sample of an IBI distribution, and you can see we've got far fewer samples there, so it looks a little bit spikier, but it does kind of follow a similar pattern. So as this shifts up and down, then we will be able to reflect it in our data. So what does that data look like? So this is the processed data. And what we are seeing here is the PPG data. So we've got the two green sensors, or the two green wavelengths, shown as these green pluses or the black stars. We've then got our infrared as a red X and our red wavelength as a blue diamond. So it might look a little bit messy on here. Now if we had sample that looked exactly like our reference profile, what we would find is that we would have a sample at the origin, 0, 0, and on the z-axis it would be at 100 if it looked exactly the same. Now we're not going to achieve that because you've seen the samples for the reference profile is made up of an entire night, whereas each sample is just one 60-second period. So, but what we do find is we get a cluster of samples. Now we can see a cluster of red, we can see a cluster of IR samples, we can see a cluster of green wavelength samples, and the other cluster of green wavelength samples right next to it, which would be expected. But what we also have are these outlier points. Now, what we can do is we can put a geometric shape around this. We can say this is our normal, and anything that falls outside of this normal, we can potentially raise an alert. The next day we could say, well, you had these measurements outside, and then we could investigate them further. Right, so I'm going to show you how this might work in practice then. So what we have here is some data from one of our volunteers who by absolute coincidence had an appointment some time ago. quite a long time ago now, to have their COVID vaccine. So what we can see is this person had a nice night's rest the night before he got the vaccine, and that is shown on the top left there as night 0, no vaccine. So we can see that the majority of the points are clustered in the top right of the graph. We can see the origin marked out with the blue lines, and it's just at the top right of there. You can see the black is clustered in one point, the greens are clustered in one point, the blues clustered in one point, and the red's clustered in another point. And now we can see the outliers on the bottom left-hand side as well. Now here's the interesting thing. The next day they went and got their COVID vaccine, and they reported feeling cold-like symptoms that night. They had a bit of a headache, a bit achy, and weren't particularly feeling very good at all. So that night they wore the health band again, and the next day checked the data, and this is the data that we got in the top right. Now we can clearly see that the data has shifted around, or around this way actually, to the bottom left, top left area, but it is significantly different from where it was previously the night before. And if we had a spherical or geometric shape around the previous night's samples, it would have set off alerts to say something was happening. So the next day, we're feeling a little bit better. They were still complaining of headaches, still a little bit achy, but starting to feel back to their normal self. Now we can see that the points that were around 100 and minus 20-ish for the black, if we just concentrate on these blacks it might be easier, has now shifted from around here up to plus 30 and around minus 50. So that's interesting. And then if we look at night 4, when they were reporting feeling much better, not quite back to the way they were, but feeling quite a lot better, then we can see that these points are now starting to migrate back to where they were before this person had the vaccine. And then what we haven't shown is at night 5, where it was very similar to this. So what we can see is we can see a reaction to something, the vaccine in this case, and we can see them going back to normal a couple of days later, which is very interesting, I think. But also it's worth mentioning that we can see these outlier samples, which might be interesting on their own. There's quite a few down here. Now this is supposed to be the night when he had a lot of rest. So we've got these here, and we've got odd points lying outside. So it might be useful if we could have a system that would show us what they are. And that is exactly what we built. So what I'm going to do now is shift over to my app demo, and I'm going to show you something that we made to process the data and to visualize the data. Okay, I hope that worked. I hope it's recording, because yeah. Okay, so hopefully you can all, well, we can see that app. So great, we can see the app that we developed, and what we can do is load this full of data from our volunteer. We've already done that to save time, but I'll just run through what we would normally do. All we'd do is open some data here, which would be our reference data, and then we'd accept the data and hit go to process it. So what we can see here is the accelerometer data from a single night's rest. Okay, so we've got our PPG. These are the two green sensors, as we saw before. Red sensors, we've got our derived heart rate. So this is our SpO2 data, which isn't calibrated, remember. And we get the power spectra for this data for the entire night. And we use this as our reference profile. So next what I do is I load in some sample data, and we get these lovely graphs where 0 and 0 is the, where is it? 0 and 0, 100 is the origin point. Now what I can do, because this is live, I can show you this moving around a bit more, and you can see that it's quite a nice geometric cluster that makes. So if you did put a nice sphere around that, we could raise an alarm or alert, or at least mark down as an interesting point to look at. This is a whole night's data, so what I can see straight away once it's plotted is we've got lots of interesting points. This is where the majority of the data lies, but we've got these outlier parts, so straight away we know there's some interesting things to look at. So what we can do is animate it, and we can see how the volunteer's heart progresses throughout the night. So what we can see is we've had a few points here very early on, and then the rest have started to cluster around this area, forming these nice patterns. And what we'd hope would be that if these would form a cluster around a small area, we could wrap a geometric shape right around that. Say anything that fell outside of it could raise an alarm or an alert. So we can see that most of them form around this area here, with a few going out and then back in again. Aside from this cluster here, which might be something worth investigating, which we probably will in a minute. So we can see it's coming out to the side a little bit here, so maybe something's changing there. Then we get one right out there in the middle of nowhere. So we can try and have a look at this one first. This is still running, and we've still got points getting. It's filled up all that in now. So this is the main cluster here, with a couple of outliers. So we're going to have a look at this outlier point here, which we can see at around 280 and 50. Okay, so what we can do is wind it back and find that exact point. We can see that the sample appears at 372, and what we can do now is we can plot that data. Okay, so first thing we're looking at is the accelerometry data, and we can see that the XYZ are pretty steady, so that means that the volunteer isn't moving around. So let's just have a look at the PPG green sensors and see if there's anything obvious there. Well, straight away I can see 2 points of interest there and there, and if we look at the first derivative, these are more obvious, and then they should be even more obvious in the second derivative. So we can see these 2 points here, which we could show to a clinician to further diagnose. It could be something that could indicate further study. Okay, so if we go back to the main data, now let's see what we've got down here in this sort of secondary cluster. So we'll have a little look at this one. Okay, so this is sample 27, which we saw was in that secondary cluster, and we'll have a look at the MPA. It seems relatively clean. There might be a point of interest here, point of interest there. Yeah, these are certainly become more obvious. Okay. So as you can imagine, we were concerned about our volunteers' health with these blips showing up in the PPG trace. So we suggested to our volunteer that they may want to see a clinician or their doctor to discuss any potential issues. It was then revealed to us that the volunteer did indeed have some form of heart arrhythmia, and had been getting treated for that arrhythmia for some time. So this is what we were seeing in these outlier patches. So hopefully you can see how useful such a tool would be to identifying issues in heart health very quickly and thoroughly. We've got through a whole night's data there, and we've isolated a few points for further investigation, and I've showed how you can potentially use this to track some form of reaction. So I think our proof of concepts phase has proved to be successful. We've shown that the algorithms we developed for intelligent monitoring can be applied to our health band data to show changes. So what we're going to do next? Well, what we're going to do next is we're going to try and further develop this algorithm. We have multiple sensors on there. We're going to combine the sensors together to give a single output. We're going to develop the health band itself further, prove the concept some more through micro trials. And how we're going to do this? Well, we're going to try and fund it through Innovate UK, public funding, private investment, and crowdfunding as well. So I hope this has given you a lot of food for thought, and I'd love to hear your opinions on the work that we've done. I'd particularly like to hear how you think it could apply to your own industries. So feel free to have a chat with me afterwards or get in touch. And there is my email there. So yeah, let me know what you think, and thank you very much for listening.